So next, what we're going to do is that we're going to work out what the Hamiltonian of this theory is. So we're going to be working out the Hamiltonian. So remember that in classical mechanics, the Hamiltonian is related to the Lagrangian by a Legendre transformation. So a Legendre transformation gives us a Hamiltonian. So you start with the Lagrangian, we subtract from it the canonically conjugate momentum times the field, then we get the Hamiltonian. So what is pi? Pi is the momentum density, and this is defined by the partial derivative of the Lagrangian with respect to the time derivative of the field. So if I look at my Lagrangian for the free scalar field, we find that phi is going to be given by, pi is going to be given by phi dot. So if we now plug in this value of phi dot, then we can define what we are going to call a Hamiltonian density, which is the quantity over which, if we integrate over all space, then we get the Hamiltonian. So this is the Hamiltonian density. So we find that the Hamiltonian density just becomes, well, there is the kinetic energy term, kinetic energy density term, and then there's going to be two potential energy type terms. One would be the spatial variation squared, the energy contained in the spatial variation of the field, and another potential energy term, which is proportional to the mass squared term. So see that the Hamiltonian density is not manifestly Lorentz invariant. So this is not Lorentz invariant. And the reason is that when we do the Legendre transformation, we have to basically take, we have to evaluate pi, which is the momentum density, and in doing that, we have to take the derivative with respect to phi dot, and that means that we have to choose a particular time slicing of our Minkowski space, and therefore, writing down a Hamiltonian or a Hamiltonian density presupposes that we have chosen a preferred time slice for our Minkowski space, and that's why the Hamiltonian density is not Lorentz invariant, whereas the Lagrangian density is Lorentz invariant because you don't have to choose a particular time slice to write down the Lagrangian density. So we can now express the Hamiltonian density in Fourier space. So what does this mean? This means that we know what the expression of phi is, and from that expression of phi in terms of a and a star, we can work out what the expression of pi is, because pi, as you remember, is nothing but phi dot, and then we can evaluate also what the the spatial derivative of phi is, and then we can evaluate what the Hamiltonian is. So the Hamiltonian has three terms, and number one, the first term is the term which is Hamiltonian density is half of pi squared, and then we can write this as an integral over both two momentum integrals, and then we have the usual factors over here. We get 2 of omega k, 2 of omega k prime, and then we have two factors of, well, here we're going to have minus I omega of k, a of k e to the power minus I kx, and then plus I omega k. Then we have a star of k. Then we have e to the power plus I kx. So these things come down from the exponential because we are in calculating pi squared. We have to take the time derivative of phi. So, and then we have a term which is exactly the same thing, except that k is going to be replaced by k prime in the second term. So this is a multiplication of these two terms. And then number 2 is the potential energy term, which is due to the deformation, the spatial deformations of the scalar field. And similarly, we're going to have the same integration measure, and then inside we're just going to have, instead of minus I omega k, the first term we are going to have I of the 3 vector k, and then a of k, and again e to the power minus I kx. Then we are going to have minus I k bar, and then a star of k times e to the plus I k, I kx. And then the second term will be exactly the same thing, but instead of k, it'll be replaced by k prime. And then lastly, we have the mass term. And for the mass term, again, we are going to have the same measure, and then we are just going to have the mass squared factored out, and then we're just going to have the usual expression for for phi. So we're going to have a of k e to the power minus I kx plus a star of k e to the power plus I kx, and then times the same thing, but with k replaced by k prime. So these are the three terms that go into the Hamiltonian. So then what we can do is that we can write so these are the three terms that go into the Hamiltonian density. And then what we can do is that we can write the Hamiltonian. So the Hamiltonian is going to be the spatial integral over the Hamiltonian density. Now, what we can see is that over here, when you do the multiplication, from the first, every term, it's going to have expressions such as e to the power I kx minus k prime x, or it's going to have terms such as e to the power I kx plus k prime x. And there could be an overall factor plus minus, but I don't care about that. And now if I do the integral with respect to the spatial part, what will happen is that in this thing, this is going to give me a delta function where this is going to be a three-dimensional delta function with k minus k prime. And then it'll be multiplied by e to the power I omega, say k, t, then minus I omega k prime of t. And over here, we are going to have, because the signs here are the same, we are going to have a three-dimensional delta function whose argument will be k plus k prime. And then we are going to have, multiplying that, we're going to have e to the power I omega k of t plus I omega k prime of t. So we're going to have those. And then what's, if I do that, what will be the expression for the Hamiltonian? Well, the expression for the Hamiltonian is a little bit long and tedious, but it's worth writing it out at least once. So I'm going to do that. So it's going to have a factor of half, and then there are two integrals over k, so we get d cubed k and d cubed k prime, and divided by the usual factor, so we get 2 pi to the power 6, and then we get 2 omega k, and then 2 omega k prime. Oh, and another thing that we're going to do is that the integral over this will actually also produce 2 pi cubed, 2 pi cubed. And that means that this factor of 1 over 2 pi to the power 6 will become 2 to the power 2 pi to the power 3. So this will be multiplying, so there will be terms such as, so there will be delta k minus k prime, and from the 3 we'll be getting the from the 3 terms that we discussed above, we'll get omega of k, which I'll just write as omega, and omega of k prime, which I'll just write as omega prime, and then we'll get say k dot k prime, and then we'll get m squared. And this term will come from the bilinear term. So the term from with ak, a star of k. And then those, as you know, will have the exponential will be of this structure. So we'll have e to the power minus I omega minus omega prime of t. And then we're also going to have terms which are a star of, one of these will be k prime. So this will be k prime. And then we'll have a star of k and a of k prime and e to the power plus I omega minus omega prime of t, bracket ends, and then there'll be the term which is the term with the delta function. So there's a delta cube here, so the delta function where the argument is k plus k prime, and then that term will have multiplying it, say omega prime, and then we're going to have, so there'll be a minus sign here, and there'll be a minus sign at k dot k prime, and there'll be a plus sign for m squared. Okay, so you should all go and check these signs, and that will be multiplying the quadratic terms in a and a dagger. So there'll be a of k, well, a k prime, and then here it's going to be e to the power, they're going to add up, so there'll be minus omega plus omega prime of t, and then we're going to have a star of k, and then a star of k prime, and then we're going to have e to the power minus I, sorry, plus I, omega plus omega prime of t. Okay, so this was a bit of a long calculation. But then what we're going to do is that we're going to do one of the k integrals. We're going to get the d cubed k prime integral. So then what happens is that, k will become k prime. So because omega is a function of k, so omega prime will become omega. So this will become omega squared. This will become k squared, and this will become m squared. So because omega squared is equal to k squared plus m squared, we are going to end up having 2 omega squared coming from the first term. So we are going to have h is going to be equal to, there's a factor of half, d cubed of k divided by 2 pi cubed, we get 4 of omega k and omega, so there'll be omega k squared here, and because of the delta function, and inside we're going to get omega k squared plus k squared plus m squared, and And then what will happen is that in this bracket, omega and omega prime will become equal. So this exponential factor just will become 1, and this exponential factor will become 1. So here we will have a of k, a of k star, and then will become a star of k, a of k. And what will happen to the second? In the second one, we see that over here, there'll be a minus sign between this guy and this guy. So in the second term, we are going to have minus of omega squared k, and then minus k squared plus m squared. But this thing is nothing but minus m squared. And therefore, whatever here is, that won't matter. This whole thing will be 0. So the second term, all these guys, they are going to just drop out. And therefore, we'll end up with a Hamiltonian, which has half of d cubed k divided by 2 pi cubed, and then we have 4 omega k squared, or omega squared, let's just call it omega squared, and then we get times over here, we get 2 omega k squared, and then we have a of k, a star of k, plus a star of k, a of k. Now, we want over here, we want the usual Lorentz invariant measure. So what we do is that this 2, cancels out one of the 2's here. So we get 2 here. And the other thing that, sorry, we don't want this index. The other thing we want to do is that I want to have only one factor of omega here. So I just cancel one factor of omega with one factor of omega here. So this is the expression for the Hamiltonian that I'm going to have. So this is the classical expression for the Hamiltonian, and we shall come back to it after we review quantization of the harmonic oscillator.